This is a sequel video to my earlier videos about RSA encryption, Intro to Elliptic Curve Cryptography. So in my earlier videos, I've talked extensively about the mathematical complexities of a cryptographic encryption scheme called RSA encryption. Elliptic curve cryptography is similar to RSA in that both are public or asymmetric forms of cryptography. If you'll recall from my earlier videos, public key cryptography relies on the strength of a trapdoor one-way function that is assumed to be easy to compute in one direction, but difficult to compute in the other direction. Instead of being rooted in semi-prime factorization like RSA, elliptic curve cryptography relies on the difficulty of calculating certain points on an elliptic curve given certain bits of information. But before we go any further, let's first define exactly what an elliptic curve is. When used for cryptography, an elliptic curve is defined as the set of points that satisfy the equation y squared mod p is equal to x cubed plus ax plus b. A and b are elements in the field K, together with a point at infinity. There also exists a restriction that 4a cubed plus 27b squared cannot equal 0. There are several point operations associated with elliptic curve cryptography that are pretty integral to being able to do cryptography with elliptic curves. The first of these operations is called point addition. So the premise of this operation is that if you have some point x and some point y on an elliptic curve, then you can execute some operations with x and y's coordinate points to attain the coordinates of a third point, r. So if you draw a line between the coordinate points of x and y, the idea is that the next point that the line hits, if you continue to extend the line, is called negative r. And if you reflect the point negative r across the x-axis, then you arrive at the point r. So now, given the coordinates of points x and y, how is it that you actually compute the coordinates of point r? Well, if we're working with some elliptic curve E that's defined over the integers modulo some prime number p, then the first thing that we need to do is compute the slope between points x and y modulo p. So the slope is going to equal the x-coordinate of point x, which we're going to denote capital X, lowercase x, or subscript x. I meant the y-coordinate of the point x, which is denoted x subscript y, minus the y-coordinate of point y, and this entire thing modulo p. And we're going to divide this by some number I, where if you multiply I by the x-coordinate of point x minus the x-coordinate of point y, then I times the x-coordinate of point x minus the x-coordinate of point y modulo p is equal to 1. So the idea here is that you need to divide by some number I that satisfies this equation. So now to actually compute the coordinates of point r. So the x-coordinate of point r is going to equal the slope squared minus 2 times the x-coordinate of point x, and this whole thing modulo p. The y-coordinate of point r will in turn equal the slope times the x-coordinate of point x minus the x-coordinate of point r minus the y-coordinate of point x, and this entire thing, once again, modulo p. So the next operation associated with elliptic curve cryptography is called point doubling. And this is pretty similar to point addition, except this time you're adding a point to itself in order to attain some third point r. So here, if you've got an elliptic curve with some point x on it, then to find x plus x, or r, you would draw a tangent line from point x and continue it all the way until you hit another point on the curve. And this is called a negative r in this case. And once again, if you reflect this point across the x-axis, you arrive at point r. Only this time, instead of being the sum of two unique coordinate points x and y, point r is instead x plus x. So in this case, the slope between x and negative r is going to be equivalent to 3 times the x-coordinate of point x squared plus a mod p, all divided by some number I, where I has to be a number that satisfies the equation 2 times the y-coordinate of point x times I mod p equals 1. And the derivation for this is actually pretty interesting. It does require some knowledge of some elementary calculus. So if you're not familiar with that, then you can just skip ahead to find out how to compute the coordinates of point r in point doubling situations. But to actually derive how to find the slope in this situation, you have to take the derivative of y squared is equal to x cubed plus ax plus b, which is the equation that an elliptic curve is defined over. So to take the derivative of this, you would first execute chain rule, so 2y times dy dx is equal to 3x squared plus a. So then dy dx is simply equal to 3x squared plus a, all divided by 2y. And as you can see, with the exception of the modulo operation, that's essentially what we've got up here. But what we've just derived right down here is just a generic equation for finding the slope of an elliptic curve, not necessarily defined over integers modulo p. And the reason that you take the derivative of this equation in order to find slope is because remember we've drawn a tangent line from x to another point at negative r. So that's why we take the derivative. So now on to finding r's coordinates in point doubling situations. So in point doubling situations, the x-coordinate of point r is equal to the computed slope squared minus 2 times the x-coordinate of point x mod p. And at this point I do have a correction to make. In a point addition situation, the x-coordinate of point r is actually equal to the slope squared minus the sum of the x-coordinate of point x and the x-coordinate of point y modulo p. But going back to our point doubling situation, after you've computed the x-coordinate of point r, then the y-coordinate of point r is the computed slope times the x-coordinate of point x minus the r-coordinate of point x minus the y-coordinate of point x, and this entire expression mod p, which actually is the same thing as the computation for the y-coordinate of point r in a point addition situation. So the next operation that I'd like to introduce is called scalar multiplication. Scalar multiplication says that if you have some point r on an elliptic curve, and you know that r is the product of some integer k and some other point x on the elliptic curve, then to actually compute r, you have to add x to itself k times. And that brings me to a very important concept, the elliptic curve discrete logarithm problem. So this is essentially elliptic curve cryptography's trapdoor one-way function. This is the equivalent of the difficulty of semi-prime factorization in RSA encryption. This is what makes elliptic curve cryptography strong. And the elliptic curve discrete logarithm problem says that if an elliptic curve E is defined over the integers modulo the prime number p, or in other words, E defined over the integers modulo p, where again p is some prime number, then given some point r on the elliptic curve, and knowing that r is the product of some integer k and another point x on the elliptic curve, then computing k is hard. And again, this is the basis of elliptic curve cryptography. This is what makes it reliable and able to be trusted. So that brings me to something called the generator, denoted G. So G is a point that is on the elliptic curve that generates something called a cyclic subgroup. Now, every point in this subgroup can be reached by repeated addition of the generator point. So if you add G and G, that's going to be a point in the cyclic subgroup. If you add G and G and G, that's going to be another point in the cyclic subgroup. If you add G and G and G and G, that's yet another point in the cyclic subgroup. And you can just keep on adding G to itself until you've eventually computed all of the coordinates in the subgroup. The order of G, which is denoted n, is equivalent to the number of points in the cyclic subgroup. And in turn, the cofactor, denoted h, is equivalent to the total number of points on the elliptic curve E divided by the number of points in the subgroup, so divided by n, or the order of G. So what I'd like to do now is show you how all of this comes together to actually execute encryption in elliptic curve cryptography. So the first thing that happens is an individual picks an equation for an elliptic curve. So let's say that this individual has picked the equation y squared mod 17 is equal to x cubed plus 2x plus 2 to define their elliptic curve. They also have to pick a generator point. Let's say g is equal to 5, 1, and compute how many points the elliptic curve has on it. So let's say that this elliptic curve has 19 points on it. The first thing that this individual has to do is generate the cyclic group. And they have to do this first by doing a point doubling operation. A point doubling operation with the point g with the coordinates 5, 1. So to generate this first point, or rather this second point in the cyclic group, this individual has to add g to itself. The first point in the cyclic group is just going to be the generator point of 5, 1. The next point is going to be g plus g, or 2g. The next point is going to be 3g, then 4g, 5g, so on, until a point at infinity is computed. And what this means is essentially when this individual tries to go in and compute the slope, their denominator is going to equal 0, and that expression is just going to be undefined. So that's where the point at infinity is computed. And in this particular situation, there are going to be 19 points in the cyclic group, so at point 19 is where the slope at infinity is computed. But first, to compute 2g, the individual has to use the equation that I introduced earlier on in this video. So to compute the slope, this would be 3 times the x-coordinate of point x, which in this case is 5, as you can see from up here, that squared, plus a, which up here, a is 2, so plus 2, and that whole thing mod p. And p in this case happens to be 17. And that's going to be divided by a number I, which satisfies the equation I times 2 times the the y-coordinate of point x, so this would be 1, mod p, or mod 17, is equal to 1. And in this case, I is equal to 9, because 9 times 2 is 18, and 18 mod 17 is equal to 1. So we divide by 9. Now the result of 3 times 5 squared plus 2, all of that mod 17, is also equal to 9. So we have 9 over 9. But what we do here, instead of dividing, is we actually multiply 9 and 9 together. Then say modulo 17. And the result of this is actually what our slope is. And this happens to be 13. So now to compute the x-coordinate of point R, this is equivalent to the slope squared, so 13 squared, minus 2 times the x-coordinate of point x, so x-coordinate of point x is 5, and this entire thing mod 17. And the result of this, 13 squared minus 10 mod 17, is 6. Now we compute the y-coordinate of point R, and that's equivalent to the slope of 13 times the x-coordinate of point x, which is again 5, minus the x-coordinate of point R, which we just computed to be 6. And that entire thing minus the y-coordinate of point x, which, if we go all the way back up here, is 1. And now this entire expression, modulo 17, and the result of this is 3. So we found that the point 2G has the coordinates of 6, 3. Now to compute 3G and 4G and 5G, 6G, and so on, we would do a point addition operation instead of a point doubling operation. But we would execute a similar process to what we just did. But I'd like to show you what happens when we try to compute the 19th point of this cyclic group, so 19G. We would go about our normal process of computing the slope using point addition. So the slope in this case is equal to the y-coordinate of point x minus the y-coordinate of point y modulo p, and we would use 18G to be able to compute this. But then that would be divided by some number I, which satisfies the equation the x-coordinate of point x minus the x-coordinate of point y modulo p is equal to 1. But in this case, 18G is equal to 5, 16. So if we call our original generator point of 5, 1 point x, and we call 18G point y, then the x-coordinate of point x, which is 5, minus the x-coordinate of point y, which is 5, is just equal to 0. So 0 mod p is equal to 1, or 0 mod 17 is equal to 1. And that's not accurate. 0 modulo 17 is equal to 0, not 1. And since this is inaccurate, when this becomes inaccurate, you know that you have computed your point at infinity, and you know that that's the end of your cyclic group. So you know that this 19th point is where your cyclic group ends. So after you've finished computing all of the rest of your points in your cyclic group, now definitively able to say what the order of G is. Remember, the order of G is also denoted as n, and that's the number of points in the cyclic group. So since we computed 19 points in the cyclic group, the order of G is simply 19. And you're also able to compute the cofactor h, which again we said was the total number of points on the elliptic curve divided by the order of g. So the total number of points on the elliptic curve, we said earlier, was 19, divided by the order of g, 19, which is just 1. Now, ideally, we want this cofactor to be less than 4 for the most secure curves, and a cofactor of 1 is ideal. So let's say that an individual, Bob, has just finished doing all of this key generation. He releases his public key, which in this case is the equation for his chosen elliptic curve, or y squared mod 17 is equal to x cubed plus 2x plus 2. And he also releases his generator point of 5, 1, the order of g, which we said was 19, and the cofactor, which we said was 1. But now he picks the first value of his private key, a value denoted beta. Now, beta has to satisfy the requirement of 1 less than or equal to beta less than or equal to n minus 1, where n is again the order of g. So let's say that Bob picks beta to be 9. What Bob has to do now is compute 9g, or the 9th term of the cyclic group that he generated. So 9g he computes by looking at a cyclic group, has the coordinates of 7, 6. So Bob releases this information of 7, 6 publicly, but he does not release his value of beta. He only releases the coordinate points of when he multiplied beta by g. Now, a second person, Alice, goes through a similar process. She computes, or she picks a value alpha. Alpha has the same restriction as beta does. 1 has to be less than or equal to alpha, has to be less than or equal to the order of g minus 1. So let's say that Alice has picked her alpha to be 3. She then multiplies 3 by the generator point of 5, 1, and finds that the resulting coordinates of this are 10, 6. Now, she also releases this information, but does not release her value of alpha to the public. Now, the idea is that Bob has his point 7, 6 released to the public, and Alice has her point 10, 6 released to the public. The idea is that Alice takes Bob's point of 7, 6, and Bob takes Alice's point of 10, 6. And Alice multiplies this point 7, 6 by her secret key of alpha, which we said was 3. And then Bob does the same thing. He uses his secret value of beta, which is 9, and multiplies that by 10, 6. So this is the secret value alpha, 3, times the point 7, 6, which is equivalent to 9g, and Bob's secret value beta of 9 times 10, 6, which is the value 3g, and this is equal to 27g. Now, since this isn't a point that we computed on the cyclic group, Bob and Alice both have to take the modulus of 27, or 27 modulo 17, 27 modulo 19, or the order of g, to get 8g. And 8g, they both find, is equal to 13, 7. So now they have this shared information that they can use how they like. So for Bob and Alice, computing the point 13, 7 is easy for them because they have the secret values of alpha and beta at their disposal. However, for some third party who's listening in, let's call her Eve, there's really no easy way for her to compute this point 13, 7 because she has access to neither beta nor alpha. And this is again the elliptic curve discrete logarithm problem. This is what makes elliptic curve cryptography strong. So although elliptic curve cryptography is starting to get a bit more attention these days, it still hasn't really come close to replacing the current crypto system, RSA. And that's mostly because elliptic curve cryptography needs to be implemented with a form of symmetric key cryptography in order to have an actual encryption scheme going on, which makes it a bit less favorable in comparison to RSA. It is said to be more efficient than RSA, but it's still in the process of gaining popularity and becoming more widespread in the world of mathematical cryptography today. Thank you for listening.